landscape of matrix versus tensor eigen problem, right? In particular, even just looking at the top eigenvalue, if you formulate that problem, look at the constraint, write down the Lagrangian, we were asking, how does this landscape differ, and can we say something more about computing the eigenvectors based on the optimization landscape, right? So to recap, first let me just quickly cover principles of non-convex optimization. I mentioned that as we wrote down the Lagrangian and started analyzing the landscape of the problems, but I thought it'll be better to be a bit more formal, right? Set up the problem. If I had, this does not work at all. So if I had, let's say, some function f of x, this is not great either. Right, so I want to either minimize or maximize this function. We were looking at first order optimality, second order optimality, and so on. Right, so the first order optimality was looking at where the gradient vanishes. Right, so all the points where the gradient vanishes. And we said that if it was a convex problem, right, this was sufficient, right, to guarantee global optimality. Because if you had convex function like this, right, so if you had the gradient vanishing, that's a unique point and that's the global optimum. But if it's non-convex, that's no longer true, right? Because you could have a problem like this. So you can have many points where the gradient vanishes, and hence this is not sufficient to guarantee global optimality, right? In fact, this is not sufficient to guarantee local optimality either. And that's when we said we should go to second order optimality, right? So if it's an unconstrained problem, so let's say I'm just minimizing this over x, let's say in some real domain, right? So in that case, all I need to look at is the Hessian, right? So if x is a vector, right, the gradient is a vector, Hessian is a matrix. So that's why we call this the Hessian matrix and the gradient vector. Right, so usually this is in some d-dimensional space, let's say. Okay, so we have gradient, now we have the Hessian matrix. So if I want this to be a minimizer, right, so locally, if this is minimizer, let's say here, if locally it means it's a minimizer, so if I make any small perturbations, right, the minimum point is this one. So in some local region, this is the minimum point, right? So if I want this to be true, then I have, sorry, do you want, someone else can switch that off? Do you want to go rest?
Okay. I'm going, it's coming in 10 minutes.
It's okay, we can, Zongi, can you
Sure.
just keep track of it, and don't worry, we'll keep it in the studio. Yeah. Great, thank you. It should be fine later on, just switching it off. So if it's a minimizer, right, if it's locally a minimizer, we want this to be positive definite. So if it's just one unique point, it's a strict minimizer, strict positive definite, right? So otherwise you may have also equality if if it's not strict. So strict means this is a strict local minimizer. And in one dimension you can see this, right? Because locally the second derivative will be positive. And if it's the opposite, right, the second derivative would be negative, and in the case of a matrix, it should be negative definite. Right, so these were the cases where you can certify, right? If you can now check the Hessian, then you can say this is now a local minimizer or a local maximizer. But then we looked at the cases where it was in between, right? So this cannot happen in one dimension, because in one dimension it's either positive or negative, right? I mean, it can happen if it's only equal to 0, right? So in one dimension, the way it happens is simply when it's equal to 0. But in higher dimensions, it can happen when it's indefinite, right? So it's neither strictly positively definite or negatively definite. So when this matrix is indefinite, meaning there are some eigenvalues which are positive, there are some eigenvalues that are negative. Right, so recall positive definite means all the eigenvalues are positive, right? Negative definite means all the eigenvalues are negative. Now when you have the mixed signs, that's when we call it an indefinite matrix, and that's a saddle point. Right, so examples of saddle points. In one dimension, as I said, it's only what we call a degenerate saddle point. So degenerate is when the second derivative is 0, right? So you have the second derivative being 0, right, when f of x is x cubed. And if you recall in the previous class, I described this, right? So if it's x cubed, here at 0, the gradient vanishes, and in fact the second derivative also vanishes, but it's neither a local minimum or a maximum, right? So it's neither. And so that's in one dimension, but to get this indefiniteness, you need to go to higher dimensions, right? And for that, you want to picture the horse saddle. So that's the reason it's called a saddle point. I'm not really great at drawing it, so you know, the horse saddle, it's like a saddle where there are some directions where, right, it's raising, and then some that are where it's descending, right? So you can picture the saddle, right? So there's some here, right? There'll be a part that where the function is increasing, and then there's another direction where the function is decreasing. So you can only have this happen in 2 dimensions or more. You can't have it in the single dimension, because there the only way you get a saddle point is when it's the second derivative vanishes, and we call such points as degenerate saddle points. And the non-degenerate saddle points have to have more than one dimension. Is this clear? Right, so like a horse saddle, you have the ascending as well as descending directions at the same point. So if you picture the middle of the saddle, right? You can go, if you go along the horse, right? That's when it's increasing. If you go perpendicular, it's decreasing. Does that make sense? So that's the intuition. So and if there is a point like a saddle point, you know, it's not a local minimizer or a maximizer, right? So you don't want such a point, because if you perturb a little, right, if your goal is to minimize, right, if you can find out this direction, it will actually keep further decreasing the function, right? All you want to make sure is you find the direction, then you can further minimize your function. And hence saddle points are not desirable when it comes to say minimization or maximization problem. Okay, but on the other hand, when we do mini-maximization or competitive optimization, we want the saddle, right? So that's because saddles are defined by this minimax requirement we have. I'll come to that later when we do competitive optimization, because for now we are only looking at one objective, right? We are either minimizing or maximizing a function. And in the case of eigenvalue problem we looked at, we were maximizing, right? So for the single objective, we don't want the saddle point, right? Saddle point is not desirable. And so that's the intuition, right? And we briefly discussed how we can get to locally stable points or local minimizers or maximizing points. And the idea was if you did gradient descent, right? So what you're doing in this case is, nothing works. Okay, this one does. So if I do gradient descent, that means I'm descending along the gradient, right, direction. So here I have like my gradient value, and I have some learning rate. Right, so this is my gradient descent. And so if I do gradient descent, what will I converge to?
The minimum? Or is this convex or not?
Just any function, right? I'm doing this on any arbitrary function.
The local minimum?
Think more. So I have not assumed anything more, right? So by definition, what are the stationary points for this gradient descent?
Gradient is 0.
Gradient is 0, right? And that's this first order criticality, right? So all stationary points are points to which gradient descent can converge, right? All first order. Right? It can converge to any of the first order critical points, right? In fact, if you initialize at one of them, it doesn't move, right? So they are stationary points for gradient descent. So what if I did Newton's method? Do people recall the Newton's update? So here, what you're doing is preconditioning with the Hessian matrix, right? So you can also have a learning rate, or you can do it with infinite learning rate if you just replace it. But we'll do different versions. What happens in this case? What are the converging points for Newton's method?
It's the maximum minimum.
So what happens if you start a Newton's method at a saddle point? Does it move? No, right? It's still stationary, so it's the same thing, right? The Newton's method can improve convergence for a convex problem, right? But for the non-convex setting, it doesn't solve the saddle problem, right? It still has the issue that if you start at a saddle point, it can still remain at a saddle point. So what's a simple way around? If I want to avoid saddle points, what can I do?
We can add some randomness, like SGD.
Exactly, right? So instead of gradient descent, if I do now stochastic gradient descent, so typically how you compute the gradient itself has noise, right? If you do it on a finite batch, that means you're not getting the exact expected gradient, right? So that is noisy. But you can also explicitly add some noise here. Right, so if you do that, then you can avoid all the saddle point. Right, what is the main intuition for this? Yeah.
Because it's random, if we perturb the system just for a small amount, then the convergence will go down to the local minima instead of the saddle.
Right. Exactly, right? So if, the problem with gradient descent is if you start at a saddle point, you just stay there because there's nothing moving you around. But if you had sufficiently random noise, in fact, if you have noise that has signal at all directions, right? That has energy in all directions, like spherical noise. Then you have some energy even in the descending directions. And all you need to do is have some finite energy there, right? Because then that'll help you find that this improves the objective function and you keep improving it. Or in other words, right, even though the gradient is 0 at that point, there is some movement along the descending direction, and then in the next step, you further use the gradient. The gradient improves and you kind of keep going on. Okay, that's the intuition. So in fact, noise is your friend here, right? So in machine learning, in a lot of ways, noise is your friend. When we talk about generalization theory, again, it comes down to noise as a regularization, right? So it doesn't always have benefit to reduce noise. For instance, in convex method, there's a lot of variance reduction methods, because the whole idea is if you're doing stochastic gradient descent, your gradient is noisy and it gives you benefit to reduce the variance, right? Because then you can converge faster if it's a convex problem. But for non-convex, it's not clear if that's a good thing, right? Because maybe you may get stuck in saddle points or saddle regions much longer because your noise was lower, right? So it's a balance in non-convex case, and that's why it's less clear what benefits you obtain in practice, right? And that's one of the reasons why beyond first order methods, we haven't seen a lot of benefit with standard, single objective deep learning problems, right?
In higher dimension, it becomes more and more common to have saddle points, right?
Yes. In fact, right, because yes, making it strictly negative definite or positive definite, right, depending on if it's minimizing or maximizing problem, is much harder, right, as you increase more dimensions. And not only that, saddles can increase when you have symmetries in the system. For instance, if you have a multi-layer neural network, so again, I won't go into a lot of details here, but I want to just quickly point this out. So if you have ReLU units here, right, you can change, there is scale ambiguity, right? I can rescale one layer and kind of divide by the scale in the other layer, and the end result is the same. Right, so there is scale symmetry. There's also permutation symmetry, meaning I can just change the labels of my middle hidden layer and I still have the same result in the end. So what this means is if you're looking at minimizing, right, there cannot be a single unique global optimum, right? There's all equivalent global optima based on the symmetries in the system. And that also increases the saddle points and the saddle regions in the system. Right, because if you have symmetries, that means there are many equivalent solutions. You can take combinations of those equivalent solutions, right? And that gives rise to saddles. Okay, so something to keep in mind. This becomes much more of an issue with deep neural networks or setups where there are symmetries. Right, so is this notion of symmetry clear here? I can do permutation, I have permutation symmetry here, right? In this middle hidden layer, I can just change the labels of the hidden nodes, right? And still the end result should be the same.
So as far as I remember from convex optimization, if we have a permutation or any other symmetry, we can reduce the problem, high dimensional problem, into a lower dimensional case. So can we apply this same principle?
Great question, right? So first of all, if a problem has symmetries, it cannot be convex.
Like for example, like a function has a permutation symmetry, so instead of
that cannot be a convex function. Because in the convex function, you only have one unique minimizer. If there is symmetries, that means there are many equivalent minimizers.
Oh, maybe I explained in the wrong way. Maybe, for example, like it doesn't depend on which way you look to the function. For example, if you look at the function from the x direction or the y direction or the z direction, the function looks the same.
Mm-hmm.
But the local minima is or the global minima is at the center. So that kind of symmetry, like a rotational kind of symmetry, not exactly the same thing.
So in that case, it's kind of degenerating, right? It could have had multiple global optima, but in that case, they all degenerate to one point, right? But in many cases, there could be, that's not the general case. In general, if you have symmetries, you end up having multiple equivalent solutions.
As long as the symmetry is not around the like optimal solution. If it's not around the optimal solution or at some other point, then it replicates the same point.
Exactly, it replicates that point, right? And that's an issue. So in some special cases, all those points, equivalent solutions degenerate to one point and you can have convexity. But in general, right, it's the symmetries that lead to even more kind of explosion of solutions. And that's why it becomes an issue. And in fact, it becomes more of an issue if you look at over-parameterized systems, right? Meaning you have now a big neural network trying to fit a less expressive function. And I'll make this more formal when we talk about generalization theory because we'll deal with over-parameterization there. But just intuitively, right, what is happening is if in over-parameterization, you have a very large network, right, trying to fit a simple function, then there are many equivalent solutions, right? Because a smaller neural network could have fit the same function, but I'm using a much larger one. So there's lots of sub-neural networks that could fit the solution. And if you've read about the lottery ticket hypothesis, that's kind of becoming popular over the last year, that talks about like having a subnetwork that would have the equivalent solution to the bigger network, right? So it relates to that, and it relates to over-parameterization. So the only comment I'll make here is when you have over-parameterization, that leads to more symmetries. Because now you can think of different subnetworks all just giving you this best possible solution or global solution, right? But you're replicating that, so there are symmetries in the system. In fact, the combinatorial number of, combination of symmetries, right? And that's why it's a lot of saddle points and saddle regions. Okay, so on the other hand, that's more expressive network, and we'll talk about expressivity in the later lecture, but in a way there's no free lunch, right? So if you make these networks richer and more expressive, they can help you generalize better and they can help you find the solution, right? But optimization will have more issues with saddle regions. But somehow you just, stochastic gradient descent seems to overcome them, right? I mean, at least in all the cases where we've seen success. But we have to kind of keep in mind that there is this trade-off that we make the optimization problem harder as we go for bigger networks, right? More higher dimensions as well as add more symmetries to the network. So that's my quick comment about saddle points and how stochastic gradient descent with sufficient noise can overcome that. So I'll come back to it in later lectures, but keep that in mind. But we'll use this now to look back at the matrix and tensor eigenvalue problems we had, right, in the last class. So we were looking at first order optimality, second order optimality, and so on. Right, so what we want to go after is the second order optimality. So let's kind of quickly recap, right, how we were analyzing the optimization landscape. But before I do that, any questions here? Right, the main takeaways were we should first start with first order optimality where the gradient vanishes. Then we should look at second order optimality because that rules out saddle points, right? And what we want are stable points that are not saddle. And if you do some variant of stochastic gradient descent or ascent if it's maximization, I can get to these strict points that are not saddle. Right, so that is kind of the takeaway. Any questions here? All good? So now, you saw this last time already, but I will, hopefully with this background, it makes more sense, right? So we had a symmetric matrix and a symmetric tensor. So it's symmetric. And we had the sphere constraint that makes it non-convex. I can just directly write down the Lagrangian. Right. And then in case of a tensor, it was a similar notion, but instead of the quadratic form, we had a cubic form, right? So again, this notion of tensor contraction, where if I contract this tensor along all the directions, I get a scalar, and that gives you the, what is the energy along that direction, right, when I contract the tensor. And that's where this notation came in handy. And then this was just kind of to, help us relate it to eigenvalue directly, right? That's why the scaling was. So I think yesterday there was the class, the recitation on tensor notations. Did you get to attend? Right, and the notes are available online too. So hopefully all the tensor notation, the contractions are clearer after that class. Was that useful? And especially the tensor diagrams, right? So tensor diagrams can, instead of writing out long summations, it can help you kind of easily represent it through these graphs. Right, so the contraction was happening along the edges, so that's a convenient way to represent different tensor operations. So anyway, keep that in mind as well, as you go to doing other kinds of tensor manipulations. So that was a comment, but yeah, to kind of go back to what we were doing in the previous class, we started looking at the first order optimality. Right, so if I had, if I wanted to take the derivative, I saw that, whenever that vanished, that was giving us the eigenvalues and eigenvectors. Right, both in the case of the matrix, this is the familiar one, and same with the case of tensor, we call them as the tensor eigenvalues. Right, and if you recall this notation, it was this tensor getting contracted along two of the directions, but the third direction was left untouched, and that's why it's a vector. right? And we had the same interpretation of stationarity in both the cases, right? If you multiply this matrix with this eigenvector, right, the direction is unchanged, and all you get is the scaling, and that's the eigenvalue. And it's the same here. If you contracted your tensor with this vector along two of the directions for a third order tensor, I get the result to be unchanged. Right? So we had looked at this in the previous class. Any questions here? All good? Right, so and then the question was, how many critical points are there? And this is where we saw a big deviation, right, between the matrix and the tensor case. So in the matrix case, because this is a linear set of equations, you had at most d solutions in d-dimensional space, right? And in fact, if there were 0 solutions, it would be even like lower than that, right? You would have this null space and then the subspace of the matrix. So all the linear algebra kind of essentially boils down to with this equation, right? So that's the starting point. But in the tensor, we said this is now very different, because going from linear to quadratic equations, you could have an exponential number of solutions for this with respect to dimension, right? And that's why thinking about this in single dimension is always not the right thing, right? Because you have now more dimensions, the problem complexity can grow. And that's why we said we cannot just hope to compute all the eigenvectors, right, and then try to pick the biggest one. Right, so the matrix case, I could potentially say, let me just compute all the eigenvectors, pick the top one, right? But but the question is which ones are stable and which ones are saddle points for this optimization problem, right? That was our hope, that even though there's lots of saddle points, if there's only few good stable points, then I can hope to run a form of right, stochastic gradient ascent, and then I can hope to find the solution. And if you recall, the matrix power method and tensor power method were variants of this. Any questions there? Right, so what we need to now do is to look at the second order condition, right, and ask whether we have strict optimality or not, local optimality or not. So let's look at it for the matrix case. So I can now do the second order. Right, so there is 2, that doesn't really matter, right? So it's m minus lambda I. So I'm looking at a maximizer problem, so what should I go for? What should I want my Hessian to be if it's a maximizer problem? Right, so we wanted it to be negative definite. Is it negative definite? At what point is it negative definite or positive definite? So there is a slight catch here, right? So otherwise I would have written it down. So the catch is we have the constraint here, right? So far what I wrote this down was unconstrained problem, right? So if it's unconstrained problem, I want negative definiteness everywhere. But if I have a constrained optimization problem, I want them only, right, like where the constraint is satisfied. So locally, I have to be moving only along the constraints, right? I cannot violate them. And for this problem, if you recall, right, so I will just write this down here, right? So the constraint was it should be on the sphere, right? So all my solutions should lie on the sphere, meaning the L2 norm is equal to 1, right? So that's where my set of solutions lie. So let's say currently I'm looking at one of the critical points or an eigenvector where my gradient vanishes. Let's say that's one of these x here, right? So if I have to move now on the sphere, what is the condition I should satisfy? Right, so this is my current eigenvector. If I have to stay on the sphere, what is the direction?
Tangent.
Exactly, right, it's the tangent or this perpendicular here, right? It's either this direction or this direction. Right, so I only need to test for negative definiteness along the constraint. Right, so meaning along the tangent. Right, so this is, so meaning along the directions perpendicular to x, right? I don't have to worry about other directions. So I want negative definiteness, right? So meaning what I want is, let's say W transpose the second derivative should be less than 0 for all W perpendicular to x. And this is the x that satisfies this to be equal to 0, right? And then for all x, and x is such that you want the first order optimality to hold. Otherwise, right, there's nothing to check. Is that clear? So more generally for constraint optimization, it's called bordered Hessian. You take the Hessian, you also look at, right, how the constraints, what are their derivatives, right? So you can, there is the notion of bordered Hessian. I won't go into it here because we won't be needing more general constraint optimization in this class. But keep this in mind. You can't just check for Hessian positive or negative definiteness if you have a constraint optimization problem. Okay, you need to look at what is known as a bordered Hessian. And in this simple case where we have just the sphere constraint, that ends up being just perpendicular constraint. So I don't have to, have negative definiteness everywhere, right? I need to only check in directions perpendicular to my x. So for what x is this satisfied? So x can be one of the eigenvectors, right? Those are the only solutions for which the first derivative vanishes. So you have all the eigenvectors for which is this inequality, satisfied? What do you think? Is it satisfied for the lowest eigenvector, meaning the one with the lowest eigenvalue? What do you think? I mean, I can write down M as sum of eigenvectors and eigenvalues, right? Let's say U is my eigenvectors. So if I have to check this, what does it mean? When I have a matrix and I'm checking, if you didn't have this constraint, first of all, right, you know how to check. Because I'm just checking a matrix minus lambda times identity, right? So I can quickly check whether it's positive or negative definite. How can I do that? I have to check if all the eigenvalues of this is smaller than this, right? Then it's negative definite. Yeah? Right? But here I just only need to check in the space perpendicular to that. For which eigenvector is this true? the largest one, right? Do you see that? For instance, if you took the lowest eigenvector, what happens? I can find a violation, right? Because all I need is the space to be perpendicular to that eigenvector. I can just pick my top eigendirection and that violates this condition. Right? So for every other eigenvector other than the top, I can always pick the top eigendirection and violate this condition. Right? So that's why it's not a strict local maximizer, it's a saddle point. And so the only one that is where this holds is the top eigenvector. So what is the outcome of this? What does this imply? We were just saying earlier, if you have a stable point, right, some form of stochastic gradient ascent can converge to that, right? And that's why matrix power method works. You get the top eigenvector if you just start from a random initialization. So if you start from a random initialization, you're making sure, right, you have some energy along the top direction, right? So the only place where that would fail is if you initialize at another eigenvector, right? Because then it doesn't move. But if you initialize at a random point, that's already enough perturbation to get you to that top direction. Does that make sense? This is the optimization of view of why linear algebra works, right? Starting with the matrix power method. Right? What it says is the top eigenvector is the only stable point, right? None of the others are. So even though this is non-convex and there's lots of saddle points, right? They're all just saddle, right? They're not local optimizers. So that's why you don't have to worry about them and you can go ahead and run the power method. Right? So you can glean this by looking at the optimization landscape.
So instead of taking the constraint set as the exact boundary, what if we take the inner of this circle to make it a convex problem?
Right, so so if you do that, then it's ill-posed, right? Because you can have all these rescalings, so you don't get the the solution as cleanly, right? Because, and that's why, I mean, there is a way to turn this into a convex problem, but it's not by making that into that region, right? So because if I make it to the region, you could make now this as small as possible, right? And you get kind of ill-posed solution there. But the way to turn it into convex problem is to essentially take the square root, like convert this sphere to a simplex, and you can write this as now essentially a linear program, and you can still solve it. And in fact, I think this goes all the way back to Toeplitz and something in 1900s. People have these tricks to do in linear algebra. So in some sense, you can explain this in a version of hidden convexity, right? Because if you did this nonlinear transform, a simple nonlinear transform, you can get a convex problem. But then there are other issues, because what's the effect of noise when you do that nonlinear transform and so on. So that's why people don't do that in practice, because you can solve it even though it's non-convex as it is. It's a good point. Any other questions here? I wish this was taught in like basic linear algebra, but at least now you see why, right, linear algebra works. Because I guess you're taught that matrix power method converges, right, to the top eigenvector. But this is really the reason why it does. Okay? Good? So with the tensor case, now we said, unfortunately, there are lots of eigenvectors. In fact, could be an exponential number of them. So what can we do by looking at the next derivative? So if you do this here, right? So I kind of now take, right, so I guess I have to do 2 times here. Right, so I take one more derivative, that is gone. So I guess there are 2. I have to check this algebra. I think it's in the notes, but in any case, right? The main difference is, in the case of matrix, you just got the matrix, right? Here, whereas in the case of tensor, you still have the contraction along one of the directions, because the result should be a matrix, meaning you're contracting your tensor along one of the directions to get the result. And I won't do the derivation here because it's lengthier for the case of tensor, but it turns out that there isn't one stable point, there are multiple stable points. But in the special case, so of course if I took a general tensor, right, it can even have rank higher than the dimension, right? So there's not much I can say about a general tensor. And if you recall, we started by looking at this CP rank, right? So there is a small number of rank 1 components that give rise to the overall tensor. Right, and if there are k such components, we said that the CP rank was k. Right, so this is what motivated us to start looking at tensors, right? Because if you recall, the mixture of Gaussians, the third order moment, right, the term that involved the means, I could write them down in terms of this CP decomposition. And the question was, can I find this decomposition, right? So that was our motivation. So it turns out, so I'll give the result. So the result is, if all the UIs are orthogonal, then they are the only stable points for this constraint maximization, right? So this aspect, so let me call this again star, right? I can have the same kind of set of points for also the tensor problem. So star has only the UI as stable points. So what do you think about this? So what's the outcome of this? If I have only the UIs as stable points, what can I do? Right, so how is this result useful to me?
We could just use the power method on tensors.
Right, because I do want all the UIs, right? I want to find the decomposition. So those are all points I want to recover anyway, right? So if I did different initializations, I can hopefully recover all these stable points, right? So that's why it's almost magical that, yes, there is more than one local optimizer, right? So the power method can give you different answers. But they're all answers that I want, right? Because finally, my goal is not just to find the top eigenvector, right? I want to find this entire decomposition. So by just looking for top eigenvector, I can also try to recover all of them. And in fact, you can speed up the recovery by doing it greedily, right? You can go first initialize, find one eigenvector, subtract it out, right, go do the others. So you can do all those kind of variants to recover this. So that's kind of algorithmic design. How do you make the algorithm converge faster? But at the heart of it is this result, right? So you can essentially write down the expansion. Here you have to substitute this constraint into this equation and check for negative definiteness along directions perpendicular to the eigenvectors. Right? So if you do that, you'll get the answer that the only stable points are components of the decomposition when you have orthogonal tensor. Right? So that's already a difference, right? Because every tensor cannot be written as sum of orthogonal components, unlike a matrix. For every matrix, I can always write it down as sum of orthogonal components. For a tensor, I don't always necessarily fit that to orthogonal components. So in that sense, the tensor is richer representation, right? I can't express it only based on orthogonal components. So if I just did sum of rank 1 orthogonal components, that's not enough to fit any general tensor. So this is a special class if I limit to orthogonality.
Can I do that if I have exponential rank?
You cannot have exponential number of orthogonal components. There's at most d orthogonal vectors in d dimensions. That's what limits this. Right? So that's why it's a very special class, right? So if you look at the entire set of tensors in say d by d by d tensors, it's a very small class that's orthogonal. Most of them won't satisfy this.
What if we do something like several different other orthogonal bases? Like instead of UI decomposition, like SVD, like UI, DI, WI.
Oh, so the asymmetric, all this also extends, by the way, right? So that's different. So, I've been looking both here it's matrix and tensor symmetric case for simplicity, right? So in the asymmetric case, it's a similar result, except that all those sets should be orthogonal, right? So if you have UI, WI, I don't know, XI, right? Like within that set, it should be orthogonal. So that's how the result extends. Right, same as in the matrix case, right? If you had now asymmetric version, you'd have X transpose MY, right? You wanted to do that, solve that bilinear problem. And you can similarly kind of write down the first order and second order conditions, and you can still argue about the top singular direction in that case. So the results go through, right? But they're more involved to kind of write down. Right, so the asymmetric holds again extends, except now you have just different orthogonal sets for the different modes. Okay, so the nice thing is if you have orthogonal tensors, I can run the power method, I can recover all the components. Right. But if you recall the goal we had in the previous class, we argued that we don't want orthogonality, right, from the notion of expressivity. If you recall the mixture of Gaussians, we were looking at the third order moment, right? Here the components were the mean vectors, right? So making them orthogonal is very weird, right? That's a very specific problem that may never occur in machine learning. If I look at data, in what scenario is the mean of one strictly orthogonal to another? I may never encounter that problem. So this by itself is not useful to solve that problem. Right, so what I need is, can I use this result to solve for general decomposition where these need not be orthogonal? Can I utilize this result but solve for a more general class? Right, so that's what I would like. And the way we do this is actually there's a nice simple trick known as whitening. So here, let's say I have my tensor that is, I'll use the notation we had for the mixture of Gaussians. if you recall, these were the selection probabilities, right, for the different components, and AIs were the means of different components. It can be other cases too, but that was one example where we wanted to find this decomposition. So we also had the second order moments, let me call this matrix M, where I had just the vectors with, only the vector product being done twice, right, instead of thrice. So I can always, of course, get M, right, with a different scaling if I take a random slice of the tensor. So if I take a random slice, I do an inner product with one of the directions, right, and the other two are still the same. So in general, you can always get even if you don't have those moments. But in that mixture of Gaussians, we had the moments, right, so we'll just use them directly. That's a detail, and we can go back to it in a minute, but let's assume I had both of these. Right, so the intuition is I have now these unknown vectors, let's say A1, A2, A3, right? In general, they can be in general directions, meaning they're not necessarily orthogonal. But what I would like to do is transform this into an orthogonal basis. Right? If I can find a transformation, I'll call it W, right, that implicitly changes this A's to these U's, then I can do the power method and recover the orthogonal components. Right, so I haven't told you how to find W, but let's say there is a magical W that gives you this transformation. Right, so what this transformation is you take W transpose AI, you get UI. Right? And let's say my system U is a rotation matrix. So meaning they are orthogonal. If I had this, then I'm done, right? Because I can run the tensor power method, I can recover the U's. But then how do I recover the A's from the U's? If this transformation is invertible, right, then I can go and reverse it. So I can say AI is W transpose pseudo inverse UI. Right, so for that I want invertibility, right? So meaning this should have full column rank because I want to invert, right, each one of them back. So if I can go both ways, then I'm done. Do you see that? So what I'm doing is if I can transform my problem to an orthogonal system, right, the underlying tensor is made up of orthogonal components. I can run the power method, and then I can just do a linear transformation on what I've recovered, and I get back my original vectors. Okay, so the question is, how do I find this? So by the way, if I had this before that, right, so if I wanted to do this transformation, I can do this implicitly. Suppose I could find a W where this is true, right, so what I can do is I can take my original tensor and do a contraction on this. So this is nothing but what I'm doing is right, so if you recall the general definition of contraction, I could extend from this being a vector to a matrix. Right, so I was like multiplying that mode with W transpose A. So this is nothing but WI. I had the weights, I had W transpose AI. Right, so that's the notation. So I can now, right, transform my underlying AIs implicitly. Right, by contracting the tensor, I can change my tensor to an orthogonal tensor. Right, so this is now equal to. right? So we haven't yet found what that matrix W is, but if I could find such a matrix that would transform it into an orthogonal system, I can turn my tensor into an orthogonal tensor, and I can recover the components. And if this W is invertible, I can get back the original A's. Is that clear? Right? So the main question is, how do you get to this? And this is where, you can, we call this whitening because I can just look at a matrix that whitens M, right? So I can look at so this is now nothing but looking at, I can find like the W is nothing but M, like square root and then minus half. Right, so in the sense and that's why it's called whitening, right? So I'm turning a matrix to identity, that's called whitening. So I'm turning an arbitrary matrix to a identity matrix. So if I do this, implicitly I'm also turning this AIs into rotation. Right, so that's why you can do the transformation without knowing what the underlying AIs are. So roughly what we're doing is we're looking at the whitening matrix and transforming our tensor to an orthogonal system. And then we can do the power method, recover, and then reverse the whitening. And in this way, you can recover the tensor decomposition for an arbitrary system. The only constraint was this invertibility, right? So for this invertibility, you want to have linear independence of these AIs, because only then is it invertible, right? If these are linearly dependent, you cannot have an orthogonal system of the same number, right? The rank, in fact, reduces. So that's why you need this to be linearly independent. Okay? In that case, you can recover the components perfectly, right? So under no noise, you get that perfectly. Any questions here?
I wonder something about the matrix case, because we write it down as a diagonal form in rank 1 matrices. So if it's a symmetric matrix, so I assume that these AIs should be orthogonal by definition. Is that so?
That's the difference, right? So in the matrix case, you can always find an orthogonal decomposition for any matrix. But in the case of a tensor, it's only a special class of tensors where you can find the orthogonal decomposition.
And the orthogonal decomposition is unique, is that right?
No.
Until up to scaling.
No, for every tensor, there doesn't need to exist an orthogonal.
For a matrix.
For a matrix, yes, but not for a tensor, right? So that's why you have that difference. And that's both the strength and the weakness, right? So the strength because you have more expressivity. You can now represent these decompositions that are not orthogonal. You have uniqueness, you can recover them, right? It was harder to optimize. If you directly try to solve this optimization problem for a general tensor, there's no guarantee, right? But if you can turn that into an orthogonal system, you're recovering only the components. And so that's why we are exploiting both the aspects, right? So the optimization becomes easy for an orthogonal tensor, but what I want is general tensors, right? Because that's when I'm going for tensor decompositions. And I can turn that by looking at this whitening transform. And when there's linear independence, I can always invert it back at the end and recover the original representation. So that's the overall scheme. So in general, this whitening transform also helps you reduce the dimensionality, right? So in the sense, this is in D dimensions. I can look at now this orthogonal system in K dimensions if the rank is K. So if K is much smaller than D, right, I have a very low rank tensor in high dimensions. I need to do this tensor power method only in low dimensions, right? So I also have better noise properties and other nice properties coming out of that. So that's also the benefit of this whitening. It's also dimensionality reduction. Similar to PCA, right? So we are also getting dimensionality reduction. Any questions here? So going back to mixtures of Gaussians, we said, we can do some modifications and get moments of this form, right? And now we can run this method in a whitening and tensor power method. I can recover the component means. So when I'm doing it in this way, first of all, there is no need for clustering, right? So I'm looking at now third order moments instead of just second order moments, right? And I can recover the component means. And even when the variance is high, I can still recover them. I mean, I would need more samples to get to this population moment well, right? Estimate this accurately. But it doesn't fail, right? It's more graceful in terms of how, as you get more samples, you can reduce the variance of your estimation, and you can get better estimation of what the component means are. Right? So that's the benefit of this method of moments, that it doesn't rely on separation for clustering problems, for Gaussian mixtures. So that's one, and the second one is in practice, right? So I have samples from my mixture of Gaussians. I don't want to compute this tensor, right? So I'm going from, let's say, n samples, each one d-dimensional, to d cube, right? So in most cases, that's now a big jump, right? So I don't want to compute this tensor explicitly, but I can do this implicitly through online tensor power methods, right? So I don't have to do this as forming the full tensor. Because if you recall with the tensor power method, what I really need is these contractions, right? So I had this. So this was the tensor power method. So I can implicitly find this contraction without forming the tensor, right? Because I can take a mini batch of my data, I can directly find the contracted answer, and hence I can, and then I'm updating my stochastic updates, right? So that's to keep in mind, like in practice, in most cases, you don't want to be forming the tensor from moments, right? So because here you're not given the tensor to begin with, right? You're given samples, and the tensor relates to the moments of that distribution. So you're better off doing the power method and other contractions directly rather than forming the tensor. And there's similar tricks in other algorithms, right? If you're doing second order methods, you directly compute Hessian vector products, in any of the packages, standard packages for optimization. You don't form the full Hessian matrix. So this is a standard trick. Many times if you directly want just the products, you don't want to be forming the big matrix or the big tensor. Okay, so this is more of a practical implementation, but to keep in mind if you're going to implement this. Any questions here?
So does it take very long time compared to the power method in matrix? It's like because I guess tiny difference may lead to very different thing, or it's like
So it really then depends on the profile, right? Both in the matrix and tensor case, it depends on the conditioning, right? So how much, so what is the lowest eigenvalue, right? You want to recover, and what is the profile of the noise, right? So that's a big question here. And it is true that the tensors or in general any polynomials will be more susceptible to noise. Any nonlinear system is more susceptible to noise compared to linear systems, right? But it really depends in practice how well conditioned the system is. And that's why the theory is more involved, right? So in the paper we wrote about using tensor decomposition for these different latent variable models. A large part of the paper was this perturbation analysis, right? Because I won't have this exact tensor in practice, right? I will have some error tensors. How do the errors propagate is much harder to reason in this nonlinear system. Right? For matrix, if you recall, there's all the matrix perturbation bounds. There's Weil and Wedin's theorem for eigenvalues and eigenvectors. Right? So we don't have such universal theorems for tensor perturbations. And we shouldn't expect to. In any nonlinear system, the nature of noise, right, can vastly determine the quality. Right? There are not universal bounds available. So in general, random noise is fine. Right, but if you're looking at adversarial noise, it's much worse to try to give guarantees for nonlinear systems. Okay, so those are some high-level comments. In the remaining time, I want to quickly talk about other latent variable models where you can compute these moments. Right, so far we looked at mixtures of Gaussians. The other day we started with hidden Markov models and we argued for spectral methods using matrices. But now we can see what we can do with tensors. And before that, I want to do the factor model, which uses will use this also in hidden Markov models. So factor model is this special case where I have this hidden variable and all my observed variables are conditionally independent given this hidden variable, right? So it factorizes the distribution. Right, so in the notation we had, right, so this would be. So here you need at least 3 observables, right? If I had only 2 observables, I can always just marginalize my hidden variable, right? So it's not identifiable. Whereas if I have 3, I can get identifiability, meaning I can uniquely recover the parameters of the distribution as long as there's no degeneracy, right? But I can't do it if there are only 2 observables, because I can just marginalize what's in between, right? It's a chain, it's just any arbitrary joint distribution of 2 random variables. So I need at least 3. Right, so if I have this, and if you recall, we can look at all of this as a discrete system, right? So we had this probabilities turn into expectations, right? So A is actually the conditional probability matrix, but I can write this down in terms of, right, expectations. So A is the conditional probability matrix. And similarly, I can, let's say, so if in the special case, right, so in general you can have different conditional probabilities for different observed variables. But in the special case, if it's the same, right, if the conditional probabilities are all the same, we call it an exchangeable distribution. Right, so and you can see that, right, exchangeable because the order doesn't matter. So if I have now, if I permute x1, x2, x3, still the distribution remains the same because the conditional probability is the same. Right, so those are called exchangeable distributions. And they have a lot of use in practice because, in many cases, I don't care about the order in which, right, they're drawn. All I care about is the overall counts of the distribution. So in that case, because of that permutation invariance, all I need to do is count, right, like how many times different values occurred for these variables, right, because the order doesn't matter. Okay, so we can do the moments even in the general case, but it's easier for the special case, right? Because in this case, I can just write down now my joint distribution of these three variables. What is this equal to? What does this computation look like? So what's the first step I should be doing here?
Can you like factorize them out because it's independent?
Is it independent?
Is it? Or
What is the catch? It's independent.
given condition.
Yeah, so you have to first condition and then take the expectation, right? So now I can factorize this out. What is the inner answer?
AH.
It's AH, right? Where else did we see this form? Have we seen this before? Saw this before, right? Where? Mixtures of Gaussian. If you recall the mean term, it was exactly the same, right? Because H was still discrete there. So we already know the answer here. So if I look at the joint probability distribution of my three observed variables, that should factorize as a CP decomposition. Right, so that's why finding the CP decomposition means I can recover them. Yeah? And this is true even if it was asymmetric, right? If you had different probability matrices, it would be just AH, BH, and so on. So you just have different, different values. It wouldn't be symmetric, but it would still be the same rank, right? So the rank is equal to the dimensionality of the hidden variable, right? How many discrete states it takes, that's what the rank is equal to. Is that clear? Right? But I wrote it for the exchangeable case for simplicity. So the other one was this hidden Markov model. Here actually there is a simple step. Right, so if I look at now three consecutive values in my hidden Markov model, what does it end up being? Right, there are many other, right, observables, but I'll just take three of them. What does it reduce to? It's already the answer. What is it? If I just look at the distribution of three consecutive random variables, how can I simplify my distribution?
Doing the same thing.
It's just a factor model, right? I can just marginalize out this variable, and I can just directly look at this factor model. Right, so what I get is now a transformation, meaning here I've marginalized, right? So I'm directly looking at how this hidden state affects the previous observed state, and how this hidden state, is related, sorry, not affects, right? So related to the next observed state. But once you find the parameters here, you can relate them to parameters here. right? So again, you need some non-degeneracy. You need this to be ergodic mixing Markov chain. Then the transition matrix will be full rank, right? So, and also you want the observation matrix to be full rank too. So in that case, you can go here, compute this, go back. Okay, so that's the method of moments for finding the parameters of hidden Markov models. So when we looked in the previous class, we argued, if your goal is only to compute the observable distribution and not necessarily look at the hidden state, you can do it through the observable transform, right? And that you can do just with matrix methods, right? With matrix spectral decomposition. But if you want to actually compute what is the transition matrix and the observation matrix, in order to infer the hidden states, you need to get to this tensor method. So that's another model we can solve using tensors. Right, so one more that's popular is called the topic model. So this has lots of good use cases. So the special one, we saw the exchangeable model with discrete hidden state. That's a special case, right? So that's also known as single topic model. So where the hidden state is discrete. But in general, the hidden state can be continuous. And the main idea is, right, you have documents and you have topics. This is the motivation. And in each document, there can be multiple topics, right? So if you take a news article, it could be about, if it's about university sports, there's sports, but there's also about education, right? So you can have not just one topics, many topics being discussed in each document. So if you want to model this, you cannot use simply, right, hidden discrete state, because that means there's only one topic in each document, right? So, but if you make this a continuous random variable, then it's multiple topics, and one special form of this is called latent Dirichlet allocation, or LDA. And what this tells you is you have a Dirichlet mixture of topics. Dirichlet is a special form of, it's a parametric continuous distribution. So you have this Dirichlet distribution of topics in each document, and for each word you first draw a topic, then draw a word, right? So roughly what it's saying is each document is made up of a mixture of words drawn from different topics. So it's mixture of mixtures, right, or admixtures. So that's the basic intuition behind LDA, right? I've obviously not written down any of the details of what the Dirichlet distribution looks like. But the main idea is if you want to go beyond, right, cluster-like models. So in the clustering model, you just have each sample belong to a single component or a single topic, right? There you can try to separate it out. But now if each document has multiple topics, there's no more any separation. Right, so you have multiple topics in the same document. You can't try to separate out as through clustering methods. Instead, we can look at the third order moments and higher order moments of this distribution, and we can also use this LDA formulation to take care of multiple topics in each document. So I know I left out a lot of details, but the main idea is you can look at these exchangeable models and come up with general distributions for age, right, that go beyond discrete to continuous distributions. And that's modeling how many topics can occur in documents. And it's also known as genetic admixtures. People use that to study in genomics when there is, admixtures or multiple topics in each genetic profile, right? So it has many uses beyond just documents and topics, but we use that terminology for this model. Any questions here? right? So the main takeaway is, for a range of these latent variable models, if you have this conditional independence or some way that the moments relate to these hidden variables, right? You can reduce the rank of those tensors, the moment tensors, using this conditional independence. Then you can use this tensor power method, whitening tensor power method, this formulation to find the tensor decomposition. You can guarantee that you will find the right decomposition. And also in practice, you can do this at scale because you don't have to compute these high order moments directly, you can do that implicitly. So these are like trying to extract the information that's present in third order or higher order moments. Okay, that's the basic principle behind this. Thank you. By the way, I have your quizzes.